So let's talk about nitrogen. It's literally everywhere. I mean, it makes up a massive 78% of the air we're all breathing right now. And most of the time, it's completely harmless, just minding its own business. But what happens when this quiet, everyday element decides to go bad?
Yeah, that's the big question, right? It's the puzzle we're going to piece together. How does this invisible essential gas suddenly become the bad guy? How does it become the main ingredient in smog, a key player in acid rain, and even a threat to our ozone layer? It's a pretty wild chemical transformation, from friend to foe.
So here's our game plan. We're going to meet the whole nitrogen oxide family, take a look at how their tiny molecular shapes define who they are, and figure out why some are basically harmless, while others are straight up environmental villains. To really get a handle on this, let's think of these molecules like a cast of characters in a movie. Seriously, each one has its own look, its own personality, and a very specific role to play in the story of our atmosphere.
Okay, first up in our cast is nitrous oxide, or N2O. This is kind of our baseline character, the one we'll compare everyone else to. So what's N2O's deal? Well, it's a simple, straight-line molecule. You've probably heard of it as laughing gas. And in terms of its personality, it's pretty chill. It's stable, doesn't really like to react with things. It mostly keeps to itself, which means it doesn't cause the same kind of direct, aggressive damage as its, let's say, more chaotic relative.
Okay, moving on to our next character, nitric oxide, or NO. And this is where the plot really starts to thicken.
Now, at first glance, it looks a lot like our last molecule, but look at that key trait. It has an odd number of electrons. And in the world of chemistry, having an unpaired electron is like walking around with a lit match. This molecule is incomplete. It's constantly looking for another electron to pair up with, and that makes it super reactive.
So there's a fancy word for this property, paramagnetic. It just means the molecule is weakly attracted to magnetic fields. But for our story, all you need to know is this. Being paramagnetic is like a chemical signal that this molecule is looking for trouble. It's a huge clue that it's not going to stay neutral for very long. And this right here is such a core concept. If you want to build an intuition for chemistry, just remember this. Molecules with an odd number of electrons are the wild cards. They're just fundamentally unstable, and they will react with almost anything to fix that. Which brings us to the true antagonist of our story, nitrogen dioxide, NO2. This is the one you can actually see and the one that's responsible for so much of the damage.
I mean, just look at its profile. Its structure is bent, not a straight line. It has that distinct gross brown color. And just like its predecessor, NO, it's paramagnetic. It still has that unstable, unpaired electron. That combination of a reactive personality and its physical shape makes it incredibly toxic, a true environmental villain. So now that we've met the main players, let's look at their personalities from a different angle. Are they neutral or are they acidic? This is a really big deal because it explains the kind of chaos they can unleash. So on one side, you have the neutral crew, N2O and NO. They've got their own issues, but they don't have that acidic bite. Then on the other side, you have the acidic ones, including our main villain, NO2. And when these molecules mix with water in the air, they form acids. And that is a huge, huge problem. And here's a really simple way to get a feel for this. The more oxygen atoms you stick onto that nitrogen, the higher its oxidation state gets, and the more acidic its personality becomes. It's a super predictable pattern. More oxygen equals more attitude. Simple as that. Okay, so we know who our villains are and we know why they're so reactive. But where do they actually come from? Well, this is where our little chemistry story slams into the real world of car engines and power plants. It's basically a two-step villain origin story. It all starts in the extreme heat of something like a car engine. That heat is so intense it actually forces the superstable nitrogen and oxygen from the air to smash together, forming our first troublemaker, NO. But that's just step one. Once it's out in the open air, that highly reactive NO very quickly oxidizes, transforming into our main villain, NO2. So what's the first thing you notice? Smog, that disgusting brown haze you see hanging over a city on a hot day. You are literally looking at a cloud of NO2 molecules. The color of the pollution is the color of this one molecule. And it's not just ugly, it's a nasty respiratory irritant that does real damage to our lungs. Then there's the sneak attack, acid rain. When our acidic villain NO2 reacts with water droplets up in the clouds, it forms nitric acid. This acid then falls back to Earth in the rain, silently eating away at buildings, poisoning the soil, and wrecking forests and lakes. It's a total slow-motion catastrophe. And finally, we get to its most devious role. Way up high in the atmosphere, its precursor, NO, acts as a catalyst for destroying ozone. Now think of a catalyst as like a chemical ninja. It kicks off a destructive reaction, but it doesn't get used up itself, which means a single tiny NO molecule can go on an absolute rampage, destroying thousands upon thousands of our protective ozone molecules.
All right, we have met the family, we've understood their personalities, and we have witnessed their crimes. So let's do a quick final lineup to see it all laid out together.
This table just summarizes our cast perfectly. You've got N2O, the pretty harmless one. You've got NO, the colorless, unstable setup guy. Then our star villain, NO2, the brown acidic gas that gives us smog and acid rain, and its even more acidic relative. Each one has a clear identity and a clear role. So we started with a simple question: how does the most common gas in our air turn against us? And it turns out the answer is this incredible story about lonely electrons, bent molecules, and chemical personalities. It's just a powerful reminder that this invisible world of chemistry is shaping everything we see. So what are you going to think about the next time you see that hazy skyline?